Okay, so this will be our last lecture. We're going to cover quite a few sections, but we're going to go through a lot of them really quickly. And honestly, this is my fourth year of teaching 1110, and we always rush through chapter 11. I think this is maybe the most thorough treatment of nuclear chemistry that I've ever given, so I don't feel too bad about sort of cramming the last few sections into one day. So the first thing that I want to talk about is a radioactive decay series. So if we look here at figure 11.5, we see how uranium-238 actually doesn't just decay to thorium. We saw that reaction on Tuesday. It's an alpha decay process. Uranium-238 goes to thorium-234. But actually, the thorium is also radioactive, and it will decay via beta decay to palladium, and then palladium will decay back to a different isotope of uranium. And that uranium will decay to thorium, and that thorium will decay to radon and radium and polonium and lead, and then it goes back and forth, lead, bismuth, polonium, back to lead, back to bismuth, back to polonium, and finally settles down on lead-206. Now this is called a radioactive decay series. And that first step, the alpha decay of uranium-238 to thorium-234, is by far the slowest step. So as soon as uranium decays to thorium, then, and that happens on a scale of billions of years, then that thorium will undergo all of the rest of the steps here much more rapidly. And I think it's on the, some of the steps are maybe 1,000,000 years. That's 1/1000th the time. So the rest of these steps are much, much faster. And some of them are very, very fast indeed. So this is a radioactive series. And, a lot of the smaller isotopes which decay will just decay once and they settle onto a stable isotope and they're done. But these larger elements are sometimes kind of far away from that belt of stability, and it's going to take them many steps to finally find themselves at a stable configuration. So this is uranium-238's radioactive decay series. Now, we talked about the different types of radiation. There are, Table 11.4. Oh, that's why. I got to go backward. I'm sorry. We talked about alpha rays, beta rays, and gamma rays. And then X-rays are just a type of gamma radiation that is lower in energy. They're both electromagnetic radiation or photons of light. X-rays are just lower in energy than gamma rays. But anyway, they're all radiation, but they aren't like all created equally. Alpha rays or alpha particles are easily stopped. They won't even penetrate 1/10 of a millimeter in water. And so if you think about something like a sheet of paper, will stop alpha particles cold. Something like your outer layer of skin, which is already dead skin cells, that will stop alpha radiation. Alpha particles are not maybe the most concerning type of radiation. Of course, if you get flooded with an overwhelming number of them, it can still be deadly. But by and large, alpha particles are easy to stop. Beta particles will penetrate further in water. 4 millimeters is far enough to get through your outer layers of skin and into the vital parts of your body. And so if you're going to be working with a substance that decays via beta decay, then you'll want to make sure you're taking good precautions. And then X-rays famously go through your skin, right? That's how we're able to use them to image our bones. And because of that, they're able to penetrate, into our bodies, and when they are absorbed, say by the bones or at a lower frequency by other tissues in our body, then they have the potential to do harm. And so you will see when you get an X-ray done at a dentist or doctor's office that the technician or nurse is going to go behind the wall and activate the X-ray machine from a completely different room, because you go in for an X-ray maybe once every many years, but they do 20 X-rays a day, and so they want to be extra careful to not expose themselves at all. And then gamma rays, can penetrate really far in water, depending on exactly how much their energy is. Gamma rays can be incredibly difficult to stop and can be very deadly. So gamma rays are the sort that require thick lead in order to stop. Okay, so those are the different types of radiation. They're called ionizing because what really makes radiation dangerous is when they start to kick electrons off of atoms. Once electrons get kicked off, atoms become reactive, and you don't want the molecules in your body to start reacting in ways they aren't supposed to. And so it's when radiation has enough energy to kick off an electron and form an ion that it becomes dangerous. Now, here we are. The way that we detect radiation is with an instrument called a Geiger counter. The Geiger counter is a chamber that's filled with a low pressure of argon gas, and it's got a wire in the center that is positively charged and the metal case on the outside that's negatively charged. Well, when radiation enters that window and strikes an argon gas atom, it will ionize it, and that causes the argon now to be attracted to the negatively charged outside, and its free electron to now be attracted to the positively charged wire. Well, that can be detected, and it's usually registered as like a little blip with a speaker. You can, of course, record a Geiger counter's signal in other ways, but just traditionally, and particularly in movies and things, the Geiger counter will be the instrument that's clicking, and the rate of the clicking tells you how frequently ionizing radiation is entering the instrument. So that's how we detect it. There's different ways to measure radiation, and you don't need to memorize these or worry about them too much, but I do want to kind of emphasize the differences between them. We have a ton of different units for measuring radiation, and the reason for that is because we really care about the different effects of radiation in different contexts. So the unit called the Curie is just simply counts the number of decay events. So it doesn't matter whether it's alpha decay or beta decay or gamma decay. None of that matters. It just counts the number of decay events. And so 1 Curie is 3.7 times 10 to the 10th decay events per second. A Curie is actually a pretty high level of radiation. Then you have the Röntgen. The Röntgen is going to measure only the ionizing events. So that's what a Geiger counter is technically counting. It's not decay events, but it's amount of ionizing intensity. So maybe some of the alpha particles don't actually ionize things. Maybe a high energy X-ray is going to cause several ionization events, even though it's just one little photon. And so the Röntgen is measuring the amount of ionization events that are generated. The rad is measuring the amount of energy that is absorbed per gram of tissue. So this would be like joules per gram of tissue. And that energy is getting close to what we care about as far as damage to our bodies. But it kind of depends what form that energy is in. For example, if I'm standing out in the sun and the sun warms my skin, then that could represent an awful lot of energy, but as long as it's not too bright and sunny of a summer day, it's not going to give me a sunburn. Whereas, a short time in a bright sun might burn me, even though it's less total energy. being absorbed than, say, a long time out in the fall sun. So the REM and the sievert are the ones that we really care about if you're wondering about your health, and they measure tissue damage. And so tissue damage is a little bit more, how do I want to say, it's like a little bit more removed from something like actual decay events and things. It's saying how much is your tissue actually damaged. That'll be a combination of how many radioactive particles are there and what types of radiation are they, what's their particular energies, etc. So the REM is what we're interested in as far as our health is concerned, and a dose of 0 to 25 REM is no detectable effect, and things get worse as it gets higher, and if you get something above 600 REM, then you're probably going to die. This is if you get that dosage over a short time period. Our body has mechanisms for repairing damage that is done by radiation, and so it's a matter of making sure that you're never exposed to too much at one given time. If we look at the amount of radiation that the average person is exposed to over their lifetime, you can sort of split it up into these different categories. And about half of it is background radiation. And so what they mean by that is things that, changing your lifestyle or where you live or anything else isn't likely to help you. So the Earth itself has radioactive elements within it, and so there's terrestrial radiation. There's internal radiation because our own bodies are composed of elements which will occasionally decompose. Carbon-14, for example. I've got lots of carbon in my body, and at least some fraction of it is carbon-14. Space, so we can't do anything about ionizing radiation that comes from the sun. The ozone layer and the ionosphere do a lot to block most of that, but some of it gets through. And then radon and thoron are parts of our constructed environment. So concrete has a relatively high abundance of radon in it. If you live in homes or work in buildings that were constructed at a certain time period in history, then you might want to test for the presence of radon. And if it's high enough, then it could actually be a dangerous place. And all right. In addition to that, you've got everybody gets an X-ray every now and again in their life. People will get nuclear therapies, so not everyone gets cancer, but on average, the average person gets about 12% of their lifetime radioactive dosage comes from nuclear medicine and things like that. So anyway, you might think that the most hazardous job from a radiation perspective is like nuclear power plant operator or a uranium miner or something like that, but it's really pilots and stewardess or flight attendants or astronauts, because they spend so much time up above the layers of the atmosphere that protect us. So for people like flight attendants and pilots and astronauts, that space wedge would be huge, and it is actually causes noticeably higher cancer rates in people with those occupations. So the last thing we want to talk about are fission and fusion. So these are completely different types of reactions. In all the other decay events, you transmuted one element into another similar sort of element, like uranium into thorium, and there was just a little extra byproduct, like an alpha particle, a beta particle, positron or something. Well, very large, very unstable nuclei like uranium-235 can also undergo a type of reaction where it breaks apart almost in half. and produces two different substantial daughter nuclei. So you see here the reaction where uranium-235 breaks apart to form krypton-91 and barium-142. What makes this type of reaction really interesting is two things. First of all, it releases a tremendous amount of energy, much more than regular alpha decay does. And it releases so much energy that if we use Einstein's relation of E equals mc squared, where energy is equal to mass times the speed of light squared, the energy lost in that system will manifest as an observable loss in mass. In other words, it's like part of enough energy was lost that it actually weighs less after the reaction. So that's the first reason why fission reactions are interesting. The other one is that fission reactions don't usually occur spontaneously. They are precipitated by a neutron joining itself to that U-235 nucleus. So a neutron, you see that careening in from the left in this figure. The neutron will add itself to the U-235. That will destabilize the nucleus and cause it to break apart. But you'll notice that krypton and barium are not the only two products. It also releases 3 new neutrons. And these 3 new neutrons are then able to go on and propagate this reaction with 3 new uranium atoms. And you can see how this is going to grow. The 1 neutron becomes 3, and the 3 become 9, and the 9 become 27, and before long you have an incredible amount of neutrons that are causing almost your entire amount of uranium to decay simultaneously. And so this is called a chain reaction. It's called a chain reaction because each step is able to accelerate the reaction rate for the next step by releasing 3 neutrons when only 1 is required for the next step. And chain reactions in nuclear chemistry are how you get big explosions. So a nuclear bomb is designed to maximize the rate that this chain reaction grows at, so that all of the energy in the payload of the nuclear bomb is going to be released in a fraction of a second. In nuclear power plants, the engineering challenge is actually to prevent a chain reaction. What you have are control rods, which are rods of different material that are able to actually absorb neutrons and slow down this chain reaction. So a nuclear power plant is going to try to keep the total number of neutrons constant. If the neutrons become too few, then the reaction stops and the plant shuts down. If the neutrons become too many, then the reaction grows very rapidly out of control. And so it's a delicate balance, and famously when it does go wrong, it can go quite horribly wrong. That being said, because of the great risk, when a nuclear power plant is designed and built, that risk is managed very aggressively. And if you consider the sum total of like loss of human life and whatnot, comparing different types of power generation, well, nuclear power fares quite well. Largely because of the poor conditions in, say, other fossil fuel extraction methods. Anyway, I don't want to get into this too much, but so that is a fission reaction, and fission reactions power both power plants and bombs and weapons. I'm pretty sure that's the last figure that we want to show, but there is one more type of reaction that we should cover. So we were just talking about fission. There is also fusion. So fission is what happens in nuclear power plants. Fusion is what happens in thermonuclear weapons, hydrogen bombs, or in the sun and other stars. Fission was taking a very large nucleus and breaking it down into two smaller nuclei. Fusion is taking two small nuclei and fusing them together into one large one. And so one example is a hydrogen plus a deuterium, which is just the isotope of hydrogen with one neutron. Well, that is going to form, let's balance this, 3, 2, helium. And then this is going to accompany a release of energy, just like breaking things apart released energy. And that may seem like a bit of a paradox, but actually the most stable nucleus is iron. And so you can always release energy by taking nuclei that are larger than iron and breaking them apart into smaller ones, or by taking nuclei that are smaller than iron and fusing them together into bigger ones. And so fusion is kind of like the other extreme from fission, and iron is really the only element that has maximized its stability and is incapable of spontaneously doing any sort of nuclear chemistry. Okay, so helium can then, you have two helium nuclei merge, and that's going to give you a that will give you a 4-2 helium and 2 hydrogens. Or you can have 3-2 helium plus a 1-1 hydrogen, forming a 4-2 helium plus an electron. A positron. So anyway, these are just examples of simple fusion reactions. These are reactions in particular that have been observed to take place in our sun. And a thermonuclear bomb is a bomb that takes advantage of fusion nuclear reactions. Now, fusion nuclear reactions require incredibly high temperatures and pressures. So if I have a hydrogen balloon, it might catch on fire and cause a combustion reaction if I'm not careful, but it's not going to undergo fusion because I'm not going to be able to achieve those extremely high temperatures and pressures inside my little balloon. A thermonuclear weapon accomplishes those high temperatures and pressures by actually having a fission explosion preceding the fusion explosion. And so by having smaller fission bombs arranged geometrically around a hydrogen sample, that's able to create a shock wave that forces the hydrogen all together and fuses the hydrogen. It's a pretty ridiculous process when you kind of think about it. And then as far as fission-powered power plants, there are plenty of people that are running research on how to do these reactions in a controlled environment for the purposes of power generation. But at this point in time, it requires so much energy just to get them up to those high temperatures and pressures that it is not an efficient process overall, and it's not economically feasible. So anyway, I think that's about all you need to know about nuclear reactions. And this is the last lecture of the class, so I'm going to go write your final exam, and you'll get to see that next week. And good luck with everything.